So quickly, I'd like to talk about our instrumental approaches to monitoring and removing drift in seafloor geodetic pressure measurements. Mark Zumberg and I have been working on this for a number of years, and just very quickly, we'd like to acknowledge a lot of our team members and colleagues in a number of different institutions. Sorry, I just don't have time to pull up all those names. Kind of as Laura showed, and this is just for context, our motivation is looking at a lot of geophysical phenomenon on the ocean floor. And she's also mentioned the axiovolcano uplift and the Tohoku co-seismic vertical displacements. But I'd like to talk a little bit more about the instrumentation themselves. And there's going to be a lot of talk about the parascientific pressure gauges, which are all basically board-on tubes. Board-on tubes are a very simple device. Think of a metal tube that's sort of bent to this sort of semicircular shape. It's filled with a pressure transmitting fluid. And as the pressure within the fluid increases, the tube tends to straighten out. This was patented in 1849. And a lot of mechanical gauges that are available today basically have the same principle. This is a board-on tube, and there are mechanical linkages, gears, a little lever that's used to detect, amplify, and display the pressure changes as determined by the displacement of this board-on tube. It works great, it's fine. The innovation of the parascientific pressure gauges is that they are still board-on tubes, but instead of a mechanical linkage, there's actually a quartz crystal that changes its resonant frequency as a function of the displacement or the strain in this quartz crystal. That means that you can measure very small displacements, resolve very small pressure changes, even over a very high pressure range itself. And there's a lot of cool things about it. There's some electronics that have to be done. You need to shock absorb it. This whole thing, by the way, is in a vacuum, but it's pretty small. This little loop here is only about 815 millimeters in diameter. And Dave Chadwell sort of tore one apart. That's what the inside actually looks like. So that was cool. We probably weren't supposed to do that. So the neat thing about that, however great it is, again, there is a lot of drift variability within the sensors themselves. Polster and all sort of wrote a seminal paper looking at a whole lot of different gauges, darts, corks, so on and so forth. And he analyzed data and showed that the average rate is equivalent to about -9 centimeters per year, 0.9 plus or minus 0.7 kilopascals per year. The thing about this graph is that there's a lot of variability between the different gauges that they've studied. It's not a zero mean process. The ensemble average of all these gauges don't average to zero. One thing, however, that is known from other data is that the drift rates do scale with the range. Higher range gauges have higher rates of drift. Lower range gauges have a lower rate of drift. I want you to sort of remember that for just a bit. The other thing pointed out by Watts et al. Is that the drift rates can vary between sensors, between one deployment to the next of the same device. You can try to pre-stress these gauges to sort of age them a little bit, but that's not a guarantee that they will behave the same way after the other. And this is a plot from Polster et al. Showing, a wide variety of behaviors for gauges. Some go up, some go down, they have different time constants. But all of them seem to behave in this linear exponential model, and that there's an initial decaying exponential term here, some time constant tau, and that's superimposed upon a linear drift rate, rate of B. And then, of course, there's the value of C, sort of a constant offset. The physical process behind all this is frankly unclear. Might be residual gas exchange, say water vapor, quartz crystal, and the vacuum chamber that it is locked into, even though the manufacturer bakes these things out at about, I think it was 150 degrees C. Might be viscoelastic creep in the board-on tube, creep in the attachment points. We've talked to the manufacturer, to Jerry Paris, and frankly, he doesn't really know what it is, though he's tried for an awfully long time. So anyway, given all of that, the approach we took at Scripps was to calibrate these systems in situ. And we went back to first principles to the standard method by which pressure gauges are calibrated. So imagine just a piston, cross-sectional area A. It supports a mass N. You put it in sort of a cylinder, it's closely spaced, and this is filled with hydraulic fluid. You pressurize the fluid in the cylinder until this piston and mass assembly is freely floating inside of that cylinder. And at that point, you have a force balance. That the hydraulic force, the pressure acting over the area A, is balanced by the gravitational force mg. That's all it is. That's all there is to it. So now the pressure at that point is simply mg divided by the area A. These are all quantities that you can go ahead and measure. And so within that system, you can take this known calibrated pressure, apply it to this pressure gauge in green here under the gauge under test. This is a pretty old process. You find examples of something like this on eBay. I have one down in the lab I've been meaning to turn into a museum piece. They date back to the early 20th century, probably the 19th century. It has a real steampunk look to it. But if you're extremely careful, modern examples of this exact same system are capable of producing pressures with a repeatability of better than, say, 2 parts per million. That's equivalent to about a centimeter of depth change in 5,000 meters. These systems, the pistons are made out of tungsten carbide. They're lapped sort of like a telescope mirror, so they have sub-micron finishes on top of them, sub-micron repeatability. And you need to take into account a number of second order effects like thermal expansion, air buoyancy, the actual surface tension of the working fluid itself. But these are all actually well understood physical processes, and they're actually readily measurable. So we decided to take one of these laboratory instruments and shove it into a pressure case, which took a while. This is an example of, this is a diagram of the schematic system. We have a pressure calibration system. It's got units, devices to basically level it, to spin up the masses. So that's kind of a point I can bring up later. Electronics to control the thing. This system has 2 quartz parascientific pressure gauges inside of it, and there are valves that allow the pressure gauges to observe either the seafloor pressure or the pressure being generated by the dead weight system. It's one of those like 3D transparent models of the thing. This is a unit under assembly in our lab here. This sphere here is like 450 millimeters in diameter. And this is another incarnation of the same device on the seafloor at axial. We're taking advantage of the infrastructure, the power and data provided by the Cable Observatory. So we have one of those great big expensive cables running off to the junction box. This is at Axial Caldera Center, for those of you familiar with the area. This is actually one of the UWA0A instruments located right next to it. This is taken, I think, 2019. Okay, so just an idea of the time series behind this idea. This is an example of a test we did off of San Diego. Most of the time, 99% of the time, the system is measuring sea floor pressure, okay, P sub T. And at regular intervals, we turn on the calibration system, generate a reference pressure, and then for approximately 20 minutes, the gauges are switched to observe this known, essentially time invariant reference pressure. Okay, by collecting a time series of these reference pressure measurements, it's going to have an apparent drift that's due to the sensors themselves drifting. From that, we can make an estimate of the drift rate of the gauges themselves in situ on the seafloor. So going back to that axial example, this is actually some data that we're working up right now. Actually, we've gone all the way up to from about July of 2018, July 6th. So in this case, May of 2021 is plotted up. We've actually got the data right up to yesterday. And you can, after doing all these calculations, this is delta P. What we show here are that for those 2 gauges within the system, we're showing the difference between what would be the expected time invariant calibrated pressure and the apparent drift of these gauges here. You can see that we're modeling not a quadratic, it should be a linear exponential model estimate. So we have the sort of decay amplitudes that are different. In one case, it's 0.8 kilopascals, 0.3. The time constants we're estimating here is say 41 days versus 28 days for these two gauges. These two gauges are about 5 centimeters apart within the same system. And they have different linear drift rates, about 0.6 kilopascals, call it 60 centimeters per year versus the other one about 4 centimeters per year, 6 centimeters.
1 minute left.
Percent difference. And then, but the residuals of all of this is something like 5 millimeters. So it's actually getting very hot. The two gauges agree with each other very, very well. Again, other people will talk about it, but we built these mobile pressure recorders. These are two commercial examples of the A08, which is essentially, you could argue, is similar to what we've done with the SCPR, except we use air pressure, one of these barometric sensors with very low drift rate. They only measure over less than 1 atmosphere. Okay, and that's one of the systems. And finally, there is another example where the Japanese JAMSTEC has a mobile transfer standard that they take from the laboratory to the seafloor, and they use that to transfer a terrestrial reference to their seafloor measurements. So the final point is that I think this is great. There's a lot of research going on into the instrumental approaches for the pressure sensor drift. But again, as Laura said, I'm sure everyone else will say that we still need to deal with the oceanographic contributions as well.